Good morning, everyone. Welcome and thank you for joining us for Teledyne ISCO's January Water webinar. Today's webinar is part of a new series that Teledyne ISCO will be running in 2019 called Ask ISCO. The Ask ISCO webinar series will allow attendees to submit questions before the webinar, and our panel of experts will then walk through the questions during the webinar. If you have any additional questions during the webinar, please utilize the chat function within the Zoom platform. Today's topic is portable sampling. Our panel of experts includes Stephen McManus and Mike Nolet, both part of Teledyne ISCO's Product Support Specialist Group. At this time, I will turn it over to Steve and Mike.
Good morning. Good morning, everyone. My name is Steve McManus, and as Tori indicated, we're here today to respond to questions that pertain to the need of portable samplers. This is not a specifically focused presentation on ISCO product, ISCO samplers, nor is it a focused presentation on any specific application need. These questions and responses are more broad in nature and apply across the board over multiple application usages, as well as just in general to not only ISCO samplers, but other samplers that may exist in the market. So the first category of questions that we're going to be responding to here relate to the questions that are more general in nature and relate to maintenance needs. We do have some of the questions that were submitted in advance. We're going to start going through those, but if there are questions that pop up and pertain to the category at the moment, please provide those questions into the chat area, and we will respond if they pertain to that particular subject. And if they pertain to a subject that we're going to cover down the road, we'll just defer that to that point in time. Any questions that we're not able to get to today in the presentation, we will go ahead, log and record, and we will provide responses when we can, and as quickly as we can. So the first question relates to what are the common projects portable samplers are used for? In many cases, the general rule of thumb for the usage of portable samplers involves application where there is not the presence of AC power, meaning you're going to need to power your equipment with batteries or a combination of battery and solar panel. These applications typically would include remote applications such as stormwater sampling, where you may have a system set up at a storm drain or storm channel of some sort, where you're going to be triggering and collecting samples based upon the event of a storm. These applications can involve moving from site to site, or they can be more permanent in nature. Other applications that would be suitable for the usage of portable samplers would be industrial pretreatment monitoring, where you may move from one location to the next on a regular schedule to periodically sample and determine what is being discharged into a collection system. They may involve the use of a process monitoring where, for example, in a treatment plant, you're taking a portable sampler and moving it through various stages of the process of treating the wastewater to discern and identify, the progress or the adequacy of the treatment process to ensure there's no problems that need to be taken care of. Again, portable samplers are typically utilized in applications where there is no access to AC power, and you typically will move the sampler around from location to location, as opposed to a more stationary refrigerated sampler, which does not lend itself to being picked up and moved from site to site by any stretch of the imagination.
So next question are, what are the benefits of renting portable samplers? Well, in essence, it's a function of the duration of the need for that sampler. In the short term, which we define as around 3 to 6 months or less, it's essentially a question of economics. It's more economical to lease a sampler for those short durations rather than making the investment of a complete sampler and all the accessories and all the outlay for future maintenance costs. So on the short term, it's simply economics. Now, when we start to approach 6 months or greater for the duration of that lease, then it would be more economical to purchase the unit. But essentially, it's a question of economics. On the short term, you're not having to buy the sampler, not having to allot for future maintenance and repair costs. Those things are going to make it a less expensive option than purchasing the sampler.
The next question comes, what is the current best management practices for cleaning used and wastewater samplers? First of all, I will always defer to the lab and whatever protocols that they're suggesting be utilized. They're the experts. They have the guidelines for specific cleaning methods. And predominantly, they understand what substances can be used and what substances may interfere with the analysis procedures. Secondarily, much of this depends upon what we are sampling for. For example, if we are testing for and looking for priority pollutants at very minute levels, one of the most easiest means of maintenance is tubing replacement as opposed to attempting to clean the tubing. And that would imply the suction line, the intake line, and the pump tubing. Some materials and substances can lead in the tubing and be very difficult, if not impossible, to remove entirely, and thus you would be placing yourself at risk of having cross-contamination and false indications of the presence of materials at a higher level than they truly are. The number one rule in sampling is that that sample in the bottle must be most representative of the constituents in the source that is being sampled from and remain in that state until they are tested at the lab. If we're attempting to determine the amount of total suspended solids, we may be able to clean the tubing simply by flushing it with a warm soapy water, followed by a DI water rinse, and that could suffice in that particular application need. Glass bottles can be autoclaved for their cleaning purposes. Plastic bottles can be scrubbed with a soapy water solution and a bottle brush, and that can be followed by a thorough rinse with DI water. Certainly after cleaning any water or tubing, you want to essentially protect that tubing from potential sources of interference and contamination from just sitting around on the shelf. So certainly put your caps back on your bottles after they're clean and dried, and maybe even cap off any tubing that you may have on the shelf to ensure that we don't have drift of particulate matter in the air, dust, or other materials that can leach into the tubing. The next question related to general maintenance and quality control tips and tricks. Again, some of this is going to be somewhat similar from the previous question, but change the pump tubing if there are any visible signs of wear and tear. Pump tubing in a peristaltic pump will eventually fail, and when you see signs of visible fractures in the tubing wall or scuffing or abrasion on the exterior, that's a sign that that tubing is getting near the end of its life. Better to replace it rather than to miss a series of samples because you've had a failed pump tubing. If you have signs of fouling, material, or discoloration in the tube, those are also signs that it's time to replace that tubing because it has the potential at that point to begin interfering with and contaminating and compromising the quality of the sample delivered to the bottle. Clean, or better yet, change your intake tube or suction line when there are visible signs of fouling. The few dollars spent on that tubing would far outweigh the hundreds, if not thousands, of potential dollars that could be misspent and that could result due to the inaccurate analysis results that would be caused by a fouled tubing. Periodically inspect the case humidity indicator on the sampler controllers to determine if the internal case humidity is elevating. This would indicate the need to recharge or better yet, change the internal desiccant packages. Use your senses. If something sounds abnormal, something probably is abnormal. Don't walk away and expect trouble-free performance if you have abnormal noises coming from your equipment. Use your visual senses. Does something look incorrect? Does something look wrong? These are signs that there might be needs for some more elevated maintenance. The question came across, what do I mean by fouling? Well, as samples are being drawn in, there is residual material that is left on the inner walls of that tube over time, and that material can begin to build up. The more material that builds up, there is the risk of some of that scuffing off and being delivered into the bottle, and thus falsely giving the indication when it's analyzed at the lab that there's an elevation of this material. That material could be biological nature, and if you're doing BOD sampling where you're monitoring for the biological oxygen demand, that material can accelerate and increase the amount of biological degradation taking place. Again, number one rule, the sample that's delivered to the bottle must represent the condition of the sample at the source at the time that that sample was collected. Anything that compromises or would degrade the quality of that sample by the time it gets to the lab, you risk, again, spending thousands, hundreds, if not thousands of dollars inappropriately because of a misdiagnosis. The other thing that's important, especially if you have an application that is more remote and more prolonged in its duration of deployment, do we have good battery charge? Are batteries going to be able to carry us through and deliver the sample that we expect? There are a couple of other questions here that have come in. Some of these are fairly simple. What is the recommended maximum fuse amperage for sampler battery leads when using a marine battery? Well, a lot of this, again, depends upon which specific sampler model is being used. Not all samplers draw the same amount of current. So my knowledge is based and steeped in ISCO samplers. So the way I would look at that, a GLS sampler when the pump is running is somewhere in the neighborhood of about 3 amps with maybe an initial surge spike of up to 6 to 7 amps. Whereas if we were utilizing one of our refrigerated transportable units, i.e. the Glacier or the Avalanche, that current could be double or even triple that. So we would probably want to go into like a 15 amp fuse, whereas a 10 amp fuse would be appropriate for most sampler models. There's a question here. Visited an injection well disposal site yesterday. It's class 1 stuff, so we cannot open it to atmosphere as a rule. Everything is closed pipe, and they will create a slip line to drop pressure something less than 10 psi. How to best plumb the suction line to that steel slip line? Well, there are a variety of ways you could go with that. Certainly a tap of some sort where you have a fitting. Probably you want to have a valve in place so that if there's need to replace tubing, you can shut down and close the line so that you have pressure-free at the sampler to be able to change pump tubing or suction line or whatever. And there's really no one right way to do it. There are multiple ways you can approach it, but there is one thing I would put out there. It is best, if you can, to have the sampler itself mounted in an elevated position above the source. And the reason for this is if the source is above the sampler will not be adequately able to freely and fully purge the line clear, and therefore you would have residual samples sitting in the line between sample events that will be degrading if it's exposed to sunlight, high temperatures, whatever. And when the sample goes to collect the next sample, it is that amount of fluid that's been sitting in the line that will be delivered to the bottle. Again, that breaks the number 1 rule. That sample will not be representative of the source that we're sampling from. Let's see here. There's a question about, have you seen or installed ISCO 6712 samplers with marine battery and solar panel? Yes, all the time. most commonly in stormwater applications that are more permanent in nature, but that's a very, very common means of powering a more prolonged or permanent location that does not have the presence or availability of AC power.
Moving on to a comparative question. One of the questions we received was understanding the differences and the similarities between the models GLS and 3710. Both the GLS and 3710 samplers are composite samplers. And by that, we mean that they only use a single bottle, meaning that the samples are indeed composited in that single container. This differs from other samplers, which can have discrete samples, placing each sample in its own individual container. One difference between the 3710 and the GLS is that the maximum container volume with the GLS is 2.5 gallons or 10 liters, whereas with the 3710, we can use bottles up to 4 gallons or 20 liters. The GLS differs from the 3710 also in that it is smaller and lighter. The idea was that it would be more easily used by field crews in transporting from site to site. 3710, with the larger capacity and the larger plastic components, is indeed larger and somewhat heavier. The 3710 also has more features, more advanced capabilities than the GLS. The GLS is really intended to be very simple to use. The trade-off there is that you do have fewer capabilities. So with the 3710, one of the things we have are pause and resumes. So we can program into the sampler to have it pause its sample program and then resume that sample program at various times. We also have the capability with the 3710 to set a specific start time, which can be useful if you want to sample in a given period of time when your sample crew is not there to start the unit. There are more advanced flow mode sampling options for the 3710. The GLS is also can be either time or flow paced, so they both share that in common. 3710 can use non-uniform time pacing. Non-uniform time pacing can be an advantage in an application where someone who's being monitored, say in industry for instance, may understand when that sampler is going to be used by hearing it go off. So if they say they hear it every 30 minutes, they can anticipate when they're sampling and they try and cheat it by discharging when the unit's not sampling. So with the 3710, we have the ability to set non-uniform time pacing so that the sample routines themselves are not evenly spaced, therefore making it much harder to cheat the system. 3710 is also capable of storing programs, whereas the GLS, the intention was to basically set up a single sampler or a single program and then simply push go. So they're both the same in that they're composite samplers. They both can use the same power sources. The type of suction line and pump tubing are identical, and the flow controls that from the external flow instrument are identical as well. So the GLS is essentially, it's a lighter weight, smaller, more simplified sampler, whereas the 3710 is larger, has some more capabilities, and can also handle a larger sample volume container.
There's a question that came in, are both the GLS and 3710 safe to use in a Class 1 Div 1 location? I'm going to expand the number of models I'm going to pump in that. I'm going to say any sampler model isn't safe to be used in a Class 1 Div 1 location. It's kind of one of those gray area questions. First of all, the sampler itself cannot be located within the rated environment. If the sampler is located within the rated environment not being rated, you have essentially just violated the requirements of that particular application. However, you can use any sampler model, including the GLS and the 3710, in an application that is rated Class 1 Div 1 by locating the sampler outside of the environment and running the intake line into the environment so that there is nothing within the environment that would jeopardize or violate the regulatory limits of that environment. There would be no spark potential for just the tubing alone. There is no electrical potential. Once the sample is drawn outside, then it doesn't matter because the electronics are outside the environment and we are not violating the spirit of the Class 1 Div 1 rating. The next series of questions pertain to application type questions. And the first question that comes on is, what are examples of where refrigeration samplers might be required? In the most basic terms, any application where there is need to cease or dramatically reduce any degradation of the sample once collected would be an application where you would likely have a requirement for active refrigeration. This commonly would fall into one of two categories. It would either be biological or chemical degradation. At times, this can also be accomplished with the use of a preservative material that would be placed in the bottle in advance, and when the sample is collected, usually in tablet form, it dissolves and it will be able to preserve the sample quality. And those preservatives are typically recommended, again, by the analytical lab performing the analysis. However, again, the focus here on this particular presentation is portable samplers, meaning there's the absence of AC power. Now, we do have refrigerated transportable or refrigerator sampler options, namely the Avalanche and the Glacier. These can be operated with either 110 or 120 volt AC source or 12 volt DC. Typically, they're going to be utilized in an application where there is a need for event-based type sampling like stormwater. So the refrigeration system is in dormancy. It's not active until the conditions met and the device that's making the decisions of the determination of whether that particular condition has occurred or not. When it says, okay, the rainfall has started, the flow has started, the pH has gone outside of the range, or whatever that particular user-defined trigger condition is, and it actively begins to sample, that is when the refrigeration system begins to fire up and operate. Obviously, when that refrigeration system is running, the current needs of the system are much greater. So therefore, if you have need for more of a 7-day-a-week, 52-week a year refrigeration system, utilizing a refrigerator in a battery-powered application is not going to be a very suitable application, simply because the need to constantly recharge and replace batteries or the need to have a very substantial solar panel system to maintain the charge of that battery is going to be in place. So typically when you're dealing with portable again, and there is the need for active refrigeration, it's going to be more of an application where there's more of an event routine where you're waiting for something to happen rather than a regular daily, 24 hours a day, 7-day-a-week sampling routine. What are better ways to keep a portable sampler, a portable composite sampler, cool in a collection container when sampling in manholes? Traditionally, the means to achieve this was to pack the base around the bottle with ice. Ice can be kind of messy because, of course, it melts, and then you have all this additional ice in the base section that may have the effect of floating the bottle, which can cause problems. And certainly it adds weight to the sampler because you have all this additional water now on top of the sample. More and more often I've run into and experienced where folks are using gel packs. One, they're less messy. They don't reuse and leave a lot of water that is collected in the base. They can just be pulled out, put back in a freezer, and then be reused. So that's a very big advantage and recommended practice that I've been passing on. Avoid placing the sampler in direct sunlight. It may sound like a simple answer, but that solar heat building up on the sampler now increases the degree of difficulty that sampler is going to have at maintaining and keeping that sample from overheating. Don't place the sampler near any sources of elevated heat, like an exhaust vent, or right near an air conditioning unit where you have a lot of hot air being blown out. If the sampler is placed within an enclosure of some sort, ensure there's some ventilation. Allow the air to pass through and allow the heat to escape rather than build up. Kind of a related question, how to ensure that samples chill while collected? Well, outside of any passive cooling method like ice or gel packs, of course, in keeping the sample outside of any source of heat or direct sunlight, that's the approach in the absence of an active refrigeration system. How do you keep portable samplers from freezing? And a related question just came in. Are there any freeze protection recommendations for the 37 or 6712s when set up in a remote location? No shelter housing available, operating off a battery. Well, one of the first suggestions I would always make, if you're going to be above ground in an outdoor type of situation, and you are operating in an environment where you do have lowered temperatures, maybe not near 0 Kelvin like we've been having the last day or so, but having an enclosure is recommended because that can add an extra layer of insulation. Not to mention that having a sampler in an enclosure adds a level of security to it, because if you have a sampler out in the open, either somebody walking by, there's the risk of them tampering with it, or even wildlife sometimes can knock a sampler over because they can be shocked, if you will, when that noise kicks off. So I would recommend, if you are deploying in an environment that's outdoor above ground, having an enclosure. If needed, there are active heating options that can be considered. They need not be any high wattage, 1500 BTU heating systems, because all we need to do is keep the sample at 33 degrees or above. Wrap insulation or heat tape, if necessary, around the suction line that's exposed to prevent little droplets of water from freezing and building up in the interior of that line. But at the bottom line, if we do have temperatures that are minus 15 degrees Fahrenheit, or even colder, Mother Nature will win without any active heating. There's only so much one can do. You can help slow it down. You can help abate the issue by adding insulation and some protection of that nature. But in the absence of any active heating source, when it gets so cold, again, there's only so much one can do. There is a question that comes in that says, is the sample temperature rule still 4 degrees C plus or minus 1 degree, or has that recently changed? I am unaware of any changing of that 4 degree mark, but again, that doesn't naturally fit in every single application situation. For example, again, if you're sampling for solids or sedimentation, that's not going to degrade if it gets warm. But if you're doing anything that's monitoring for and evaluating the biological and chemical effects, in those particular situations, you do want to have that sample chilled, and the target is 4 degrees C. There are questions came in. What are some examples of enclosures? Are they homemade or can they be purchased? Basically, an enclosure is a box that's big enough to house the system. They can be very fundamental and homemade type boxes with plywood, maybe had a little insulation on the inside. I've seen enclosures that folks have made that were 3/4 inch thick steel, because the samplers were being deployed in areas where there was a lot of hunter activity, and they became targets for frustrated hunters, and they wanted to protect the sampler. There are fiberglass enclosures that are very finely and custom made out there from a variety of manufacturers. So an enclosure is, in its most basic form, is just a box that houses the sampler. It need not be any high pollutant, fancy, enclosure, but they are available, and it doesn't take long to look around. Can portable samplers be used for automated sampling of stormwater runoff on ephemeral streams that exhibit flashy runoff and high sediment? At its most basic answer, yes. Samplers are many sampler applications are stormwater in nature. And they would incorporate often not just a sampler, but a flow monitoring device, certainly a rain gauge that is able to establish that there is a rain event underway to release and allow the sampler program to run. If you have really high, flashy, short, bursty type flow application conditions, that external equipment will also be very important to be able to establish and inform the sampler that, hey, there's water here, take a sample now, or there isn't any water here, so don't bother because you're just going to collect air. Pump flow applications are very similar commonality, where you may have a line downstream from a lift station that, on some irregular basis kicks the pump on, pushes the flow down the pipe. When it drains the wet well, it turns the pump off, and eventually the flow subsides to nothing. So in those applications, you would want to have some sort of means of determining the presence of fluid that to be able to sample, and not just the presence of fluid, but adequate depth to make sure that it's going to be able to pull in sample as opposed to air. If the depth of water is insufficient to fully and adequately submerge the intake strainer, given the choice of drawing in air or drawing in water, air is going to win every time, and you're not going to be able to collect samples. And in the end, you're just going to increase and accelerate the decline of your battery charge unnecessarily by missing samples. Again, related questions, stormwater sampling, rain activated. Absolutely, again, for stormwater samples, portable sampler is a very common and popular product to use in that application. And again, we do have the need to have the means to be able to inform the sampler that, okay, it's raining, I have the runoff, start your program. Now, some samplers have this capability built in, and from an ISCO perspective, that would be a sampler like the 6712 or the Avalanche, where there is a rain gauge input, so that we can program the sampler directly to monitor that rain gauge, and when a sufficient amount of rainfall is detected within a certain duration, it can be used to trigger the sampler into operation. Again, we also have often find the need to add in the measurement of flow, or more importantly, depth, so that we can track the amount of water that's going by, and that can be used in post-analysis of the sample collection to determine the amount of flow, and then correlate that to what was found in that particular sample that was collected at that moment in time.
So on some devices, you also have to have that external device. 6712, for instance, or the Avalanche can take that direct rain gauge input. Other ISCO samplers can also be set up to trigger a sample routine based on rainfall and or level by use of an external device. So really, any ISCO sampler with the appropriate hardware can be configured to be activated based on a rainfall condition.
These two questions are essentially related to one another. They pertain to mercury sampling, and they kind of bounce around what are the best sampling practices for mercury, and I would even broaden this to say in metals in general. Rule number one, when it comes to sampling for metals is you want to eliminate and remove any metal components that are in the sample transport. That means the intake line, the strainer. First of all, the strainer, you would want to utilize a strainer that is no metal whatsoever. Any tubing couplings that you have to join the suction line to the pump tube, you would want to use a non-metal material. In some samplers, we have a bulkhead fitting that feeds the sample into the compartment where the bottle is located at. That may be a stainless steel. You would want to remove that and switch that over to a non-metal material. And the purpose for that is if you're testing for metals, why would you want to risk elevating and falsely elevating the presence of metals because you have sample in contact with metal? The second point that you'd want to avoid is the use of any glass bottles. And while not all glass bottles have lead content, i.e. metal, why risk it? So you would want to use plastic bottles. Do not use glass bottles because there is at least the potential for presence of metal. Now, any portable sampler could be utilized in that application. Frankly, it could also be a permanent refrigerator for that, but the same rules would apply there for a more permanent stationary unit where you would want to eliminate any sources of metal in the sample transport and utilize plastic bottles. There was a question that came in here that pertained to the previous question about stormwater sampling. Is there any way to prevent debris during stormwater sampling? Well, in a nutshell, no. Stormwater, especially if you have a good gully washer, is going to wash off debris. The best things you can do is be very logical and determined at where you place your intake line. If you happen to see that there's a location in that channel where there is more of a preponderance of debris, don't bother or avoid placing the strainer into that location. Find a location where there is less debris, maybe some natural barrier that would divert debris around the intake strainer. Certainly there can be artificial means of being able to divert debris around. Something as simple as a diversion plate of some sort out in front of the strainer to shed and move debris off to the side so it doesn't collect up on the strainer. And that's not just true for stormwater. That would apply for any applications because you can have, sewage lines that have more of a presence of debris than others. The next series of questions pertain to questions that are more programming in nature. And the first question is, can you provide general recommendations on programming and calibrating? Now, it's certainly difficult to provide any specific answer on programming because each application need will dictate a variety of specific program or configuration options that must be selected. Those options can be very broad in range, and not every application would be able to utilize any given programming or configuration option. So that would be the first question, is understand what you're doing, why you're doing it, because that's going to drive what you select in your programming selections. There are some basic things that can be indicated, such as, again, know what you need, know what the conditions you are being asked to operate in, as this impacts those programming decisions. For example, if you're doing flow pace sampling, obviously there are certain things that you need to understand to be able to configure it. At the top of the list, you need to have a flow meter. You need to have some means of monitoring flow so that there is information available to the sampler that's flow based. There are times when I've fielded a question on the phone and somebody's trying to program a sampler up for flow-based programming, but they don't have a flow meter. Well, it's pretty tough to flow pace a sample in the absence of that flow meter. Then you also need to make the determination or have the knowledge of, is flow in this particular location I'm sampling from continuous, or is it more periodic in nature? That's going to dictate some of your program selections. This is also very important when you're, again, sticking on the trend of flow-based sampling. You need to know information that pertains to your average daily volume. You're going to set this program up to typically take flow-based samples over a 24-hour period of time. Therefore, you're going to need to determine at what intervals you want to collect your flow-based samples. And you want to make sure that whatever that configuration setting that you end up at putting into the unit is going to be able to cover the full 24-hour period. And at the end of that full 24-hour period, you want to ensure that there's adequate volume in the bottle collected that allows your lab to do the analysis that you're after. Well, that necessitates knowing what your targets that you're working around are for your average daily flow volume. It's also important to know if that flow meter that's there, what type of flow signal is available. Is it a contact closure? Is it a voltage pulse? Is it a 4 to 20 milliamp signal? And after you understand and know what type of signal you have, what does that signal represent? If it's a 4 to 20 signal, is it 0 to 100 gallon per minute? Is it 0 to 500 gallon per minute? Because that's going to drive and dictate how you configure the sampler up to sample appropriately based upon what you need it to do. My rule of thumb is to configure the unit such that on an average flow day, 96 samples are going to be collected, which works out to be an average of 4 samples per hour. I will also configure the unit so that in the event that I have an above average flow day, I have room left in the bottle to collect more samples as a result. Now, if the range of flows in a given application are very wide and highly variable from day to day, it may be very difficult to do a true flow-based sampling. Because if some days you have 3,000 gallons of flow and other days you have 1.5 million gallons of flow, there's no way you're going to be able to devise a flow-based program that's going to be suitable for that range. That might dictate that you fall into doing, again, time-based sampling, but that you would then do some post-collection compositing where you flow weight the amount of samples based upon the flow rates that were monitored at that point in time throughout the day. Whereas you would have each sample and you would have the flow rate for that was going on at the time that sample was collected, you would be able to siphon off sample from that so that if you lined up all the samples collected over that 24-hour period of time, the level in the bottles would equate the flow curve over that full day. Question, how frequently should sample pools for a composite sample be set up? Well, again, there's a measure of user choice here, as well as whatever is dictated by, the edicts that have, generated the need to collect samples in the first place. But in general, my rule of thumb, again, falls back to that every 15 minutes for time-paced, which equates to 96 samples over the day. And as indicated above, 96 samples on an average day. If I'm doing flow-paced samples, I will devise a program to meet that target. But that's not an absolute need. Those are just my rules of thumb. That certainly can dictate from application to application, as well as from particular requirements that have been established by whatever is the entity that's dictating the need to collect samples in the first place. Question here about what behavior should you expect with a machine when doing calibration, especially coming from a major change from a previous programming. I assume that question means, well, if I'm collecting 100 mil samples and one of my normal operating procedures is to validate the accuracy of the volume delivered before moving on to the next task of the day, and suddenly I find that whereas yesterday and the day before I was, getting within that 100 mils plus or minus 10 mils. And today I went out there and suddenly I'm only getting 25 milliliters, or I'm getting 200 or 250. If you have a unit that has a liquid detector, the things I would start to look for with that, is there any potential source that could interfere with that ability of that liquid detector to sense the presence of liquid? Do we see air slugs getting pulled up in the line? Is our intake fouled or blocked or restricted to a point to where the efficiency of the pump has dropped way off? Have we had any physical damage to one of the suction line or intake tubing, or where maybe some critter decided to gnaw on it and created a little hole? I've had that happen on more than one occasion. Is our pump tube beginning to wear out and show extreme signs of fatigue, which would obviously impact the efficiency of the pump? Is there material built up or debris built up on the roller surfaces or in the pump housing itself that could be inhibiting the efficiency of the pump? That falls back into one of the answers I had given earlier about use your senses to discern that, hey, there's something going on here and I need to investigate it. In this case, getting a significant deviation on volume delivery would be one of those cases where you want to take a look at everything. And don't rule anything out until you've actually physically ruled it out as not being an issue. That kind of feeds into the next question here about how does the relationship of the liquid detector and the peristaltic pump rate correlate to actual sample collection? Well, in the case of the peristaltic pump, the rate or speed of the pump is what I'm assuming to be the crux of the question here. The transport line velocity is certainly impacted by the speed of the pump, among other things such as the length of your line, the lift, the viscosity of the fluid, the amount of debris and material in the flow the fluid that you're pulling in. But once liquid reaches the pump, the volume that is delivered is very consistent for each revolution of the pump. It's roughly 10 milliliters for each half revolution of the pump. Therefore, once liquid has reached the liquid dispenser and it knows it's there, and that would also mean it's just reached the pump, the unit monitors the pump revolutions. It's not based upon an amount of time that it operates, it's based upon the number of revolutions. And so if we have indicated a desire to deliver, for example, 150 milliliters of sample, that means that once liquid has been detected to have reached the pump, the unit switches over to the bottle fill or sample delivery mode that says, I need to make 7.5 revolutions of the pump to deliver this 150 milliliter sample. That kind of ties back to the question that was just asked about, deviations. So for example, one of the things that will impact that consistency or that accuracy would be fatigued pump tubing. Pump tube that's wearing out, tube that's beginning to, develop fractures in the wall, or be severely abraded. It's gotten to the point to where it's, deformed and it's more oval rather than round in shape, so it's not springing back to shape after the rollers pinch it, which is where the vacuum is developed from. When you see that, change the pump tube. Don't and never run the pump tube to the point of failure. Okay, there's another question here related to programming. When I change a parameter on a program, it is not saved for the next. How can I save the change? That question really, at this point in time, is not specific enough or detailed enough for me to be able to provide a direct answer to it, but I can answer in general. If, for example, you change the interval time between samples from, say, 15 minutes to 30 minutes, it should save and maintain that setting. If you change the volume delivery, If you change it from, say, delivering 100 mil to delivering 200, it should save and make that change should still be present upon next use. Now, if the question means that I go out and I deploy the unit and I had a program put in and I take it back to the office and set it on the shelf for a few days and take it back out, and when I've powered it back up and at the next deployment, my observations are that everything in the program is reverted back to some default setting, not what I entered in the last time. That could be an indication that the internal lithium battery has gone bad in that unit and it's unable to maintain and save and preserve those program settings when external power is disconnected. We got a few more questions here. We're going to be moving into the next area, which is the questions that relate to installation.
So regarding installation, a question comes up is, how can you securely hang or place a portable sampler in a manhole for 24-hour sampling, collecting composite samples in low-flow situations? Well, with respect to placement or hanging the sampler, ISCO does have what we call a pro hanger and a suspension harness. Those two devices used in conjunction physically suspend the sampler above the manhole invert. It's also possible to develop your own hardware to do that. There are eyelets, there are anchor points on the portable sampler that allow for the easy use of any kind of mounting components. Some things to ensure when doing this is that we have to anticipate the increased weight of the portable sampler once we have water in the sample container. So water is pretty heavy, and if you have a 3710 with a 4-gallon bottle in there and gets most of the way full, the change in weight will be significant. So the operator will certainly want to anticipate that. Making sure that the sampler is level. That's very important also. We don't want it yawed one way or the other. That reduces the likelihood of our sample liquid spilling, also decreases the likelihood of our discharged sample liquid missing our bottles altogether. We also want to keep our operator in mind. So we have our sampler in place. The added weight there not only has to be accounted for with respect to the hardware, but the person that's going to lift that sampler also has to be taken into account. So we want to make go to reasonable lengths to make it easy to remove that sampler from the location when our sampling collection is completed. Power supply options for manhole applications. Here, we're pretty much limited to batteries. Most codes and regulations would indeed prohibit use of line power or 120-volt power in a manhole environment. Getting off on another question regarding whether or not to use NiCad or lead-acid batteries, each of those will have different advantages. For short-term needs, where we're sampling on a regular basis, NiCad batteries are probably going to be a better option for you in that you'll get more charge-discharge cycles out of a NiCad over its life. Additionally, it charges more quickly than a lead-acid battery does. And it also is less prone to the effects of cold temperatures. Lead-acid batteries, our lead-acid batteries do have a somewhat higher capacity. They are also a better choice for what we call standby power, where the sampler is in a location, we're waiting for the sampling conditions to exist at some unforeseen time. When that condition arises, we want to ensure that our power source has enough energy to be able to power the sampler for that duration. A lead-acid battery has very good charge retention, whereas a NiCad will generally discharge at a rate of about 2% of charge voltage for 24 hours. So for regular sampling, the NiCad is probably a better choice. For stormwater sampling or something similar where we need standby power, the lead-acid is going to be probably the best choice for us. Now, for longer term needs where it's not possible to have as many folks come in, that's where probably a deep cycle marine battery and even a solar panel charging system could be used to get greater continuous power in a remote location.
We're starting to get close to the end of our time here, so I'm going to filter down to close things out here to a couple of 2 or 3 final questions. There was a question from the audience that said, should you ever turn the liquid detector sensor off? The answer to that is absolutely. If you're in the application condition that's going to work contrary to that liquid detector, i.e. applications that have high degree of entrained air into the sample, applications where you have a fairly significant vertical lift, 23, 24, 25 feet, applications where you may have high degree of viscosity in the sample that's being collected. All of those situations are examples that will defeat and work against the liquid detector. If you were to keep the liquid detector active, then that you would get pretty much a bevy of errors being reported, and you may have a lot of variance and inaccurate sample collection. I'm going to leave the top question alone for now, the reliability of alternate power, because it's somewhat of a nebulous question. But I'll just say that we can power our systems from any 12-volt source, regardless of what that 12-volt source is. But the next question is a little more pertinent in nature about discussing the battery life. How can we get the most out of it? Well, regardless of what application condition we're in, the size and capacity of the battery is very critical in being able to answer that question. The more the capacity of the battery, the longer it's going to be able to power the system. The smaller the capacity, the less time it's going to be able to power the system. The next thing is programming and configuration selections are critically important when it comes to battery life, because how you program that sampler will have a tremendous impact on the usage of that battery. If you put line rinses in, if you tell it to collect samples every 5 minutes as opposed to every 15 minutes, that's going to accelerate and increase the amount of drain on that battery. So make those decisions very carefully. If the deployment of the sampler is more long-term in nature, go big. Go with the deep cycle marine battery. More power than you've actually needed is always preferred over not enough power. But even then, if you go with a big marine battery, your configuration settings have huge impact on power. So make those decisions very carefully. If the deployment is more permanent in nature, you might want to have a solar panel in the mix to make sure that the battery charge is maintained at all times. The last question I'm going to answer for our time here today, what are common installation issues for automated samplers, and how do you solve? And these questions and these answers are just based upon my experience over the last 35 years. A very common problem for sampling, especially as it pertains to volume delivery accuracy and associated issues, is locating the sampler below the source. As indicated earlier, when it comes to that purge, it's not able to vertically purge that sample, so you have retention of fluid in the line, and it's that fluid that's retained in the line that gets sampled. If you have a lot of solids in the sample source, those solids will collect at the pump and could cause potential issues there when it starts to operate the pump, if there's a lot of silt and sand or sediment at the pump rollers. Another one, unnecessarily configuration settings that have accelerated battery drain. Again, examples, line rinses, highly intense sample routines, highly intense measurement intervals for parameters if you have a flow or other parameter component with your system. Improper consideration of the needs of the application conditions with programming the samples, resulting in missed samples. If you're in a pump application where you may have kind of flashy periodic flows and then followed by dry pipe, if you just put up a 15-minute sampling routine, chances are great, at least 50-50 or worse, that it may attempt to collect samples when there's no fluid in the pipe. Very common one, pump tube replacement. Someone's changed the pump tube, and now all of a sudden the pump isn't performing as it used to, giving liquid detected errors, failing to deliver accurate volume. The pump tube was put in backwards when it was replaced. Improper intake placement that fails to ensure full submergence. So if it's not adequately submerged, it's elevated, and at times it's even exposed to air. That will prevent the collection sample. Lack of maintenance procedures, namely regular tubing placement. These are things that can contribute to and cause problems with the quality of sample that's delivered to the lab. Now, as indicated, that was the last question I was going to take or answer for our presentation time here. I assume we're going to be able to receive questions for a period of time here, even after the presentation has been completed. So if you do have questions, please continue to submit them. We will provide responses to those questions. We thank you for your presence today. You can contact the product support group anytime you have questions. Our direct line into the department is 866-298-6174. Questions can also be submitted via email, iscoeps@teledyne.com. And once again, I'd like to thank everybody for joining us here today. It's a pleasure to have you there, and these are always kind of fun to pass on and share knowledge.
Yes, and I want to thank both Steve and Mike for going through these questions today. Obviously, there are a few that we did not get through. We had so many questions come in, so thank you for submitting questions when you registered. We've been recording these questions, and we'll work through them after the webinar and get to what we can. Again, there's contact information if you have further questions afterwards. After this webinar closes out, I do want to let you know that a window will pop up to take a survey. This is our first Ask ISCO webinar that we've done, so we're always looking for ways to improve and things that you might recommend us do differently in the future. So we're welcoming that feedback, and we want to make sure that this is an enjoyable experience for everybody attending. I do also want to let everybody know that our February webinar will be focused on things to consider in collection system flow meters. So if this is a topic that interests you, be on the lookout for an email invitation to register for that upcoming February webinar. This webinar has been recorded and will be available to all registrants and attendees later on this week. You will get an email with the recording of the webinar. Again, if you have any questions or comments, there's contact information on the screen, and we want to thank everybody for joining us today. Have a great day.